In this video, we will focus on two domains found in the Common Core State Standards for Mathematics. Those two domains are the counting and cardinality domain and the number and operations in base 10 domain. In the CC strands, children learn to say and write small counting numbers and to count collections of things. In the numbers and operations strands, students learn to use the powerful base 10 system. Although there are many types of numbers, the most basic numbers, the numbers that children usually start with, are known as the counting numbers. Counting numbers begin with 1 and continue up to infinity. We mainly use these numbers to tell us how many or how much of something, and able to communicate or give detailed information about a set of objects. Now, when we come to thinking about the set of objects and how these counting numbers work, we need to stop and take a look at two different views of counting numbers. One way to think about the counting numbers is as a list. The list of counting numbers starts with 1 and continues, with every number having a unique successor. Except for the number 1, every number in the list has a unique predecessor. So, the list of counting numbers is an ordered list. Every counting number appears exactly once in this ordered list. The ordering of the list of counting numbers is important because of the second way of thinking about counting numbers. The second way to think about counting numbers is telling how many. In other words, a counting number describes how many things are in a set. The number of things in a set is called the cardinality of a set. Stop and think for a moment about how abstract the idea of cardinality is. We use the number 5 to quantify a boundless variety of collections. We could have 5 cats, we could have 5 toys, we could have 5 jumps, we could have 5 claps, and so on. The number 5 is abstract. It's a common aspect that all the examples of sets of 5 things share. For sets up to about 3, 4, or 5 objects, we can usually recognize the number of objects in the set immediately without counting the objects one by one. The process of counting the objects in a set connects the list view of numbers to the cardinality view. As adults, this connection is so familiar that we are usually not even aware of it. But for children, this connection is not obvious, and figuring it out is an important milestone in their development. When we count a set of objects one at a time, such as this picture where we're counting blocks, 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks, we are making a one-to-one correspondence between an initial portion of the list of counting numbers and the set that we are counting. In this example, that means that every number, exactly one number, is paired with exactly 1 block. But there is another critical piece of understanding this connection of one-to-oneness that we as adults typically take for granted, but it's not really obvious to young children. The last number we count tells us the total number of objects in the set. So looking at this example, there are 5 blocks in the set. This is why the list view of counting, where each number has a unique successor, and every number except 1 has a unique predecessor, that list view of counting numbers is so important because it makes the connection between one-to-one correspondence, counting, and cardinality. If we take a brief divergence and think about where our digits for our numbers come from, it's really quite interesting. And if you think about it, the numbers that we use, 1, 2, 3, 4, 5, our counting numbers, have just been handed down to us really by tradition. 4 doesn't have to be the number 4. 4 could be represented by 4 tally marks. Or it could be represented by the Roman numeral of 4. There are multiple ways to represent 4. So why do we stick with what's been given to us, which are the digits 0, 1, 2, 3, all the way through 9? These 10 digits can form all of the numbers that we use because we use the base 10 system. And in the base 10 system, name that because we have 10 digits. In the base 10 system, place value is what determines the cardinality of the set that we're looking at. Place value for our purposes can be defined as the quantity that a digit in a number represents. And if it's the quantity that a digit in a number represents, then that means it depends in a very, very specific way on the position of the digit in the number. For example, the number 2 right here tells us that we have 2 things. But if I move the number 2 to here, this 2 represents 20 things. If we move to another number, then this 2 now represents 200 things. So the position matters. While we know as adults that 10 plays a very, very special role in the base 10 system, to children it's not so obvious. Children extend their understanding of the base 10 system in 2 ways. The first way is viewing a group of 10 as a unit in its own right. And by understanding that in a 2-digit number, the first number represents the number of tens and the second number represents the number of units. And that understanding can be represented with bundled objects or a simple drawing. For example, if we take the number 27 and we wanted to do a simple drawing of it, we can have the students show the tens place by putting 10 dots, 10 stars, 10 whatever they want together as bundled units. And then showing that the 7 is not bundled together. So this is 2 tens and this is 7 units. As students' understanding of place value continues, they'll realize that just like units, values of 1 units can be grouped together into bundles of 10, then 10 bundles of 10 can be grouped together to form 100. And 10 bundles of 100 can be grouped together to form 1,000. And from that, the base 10 system really shines. Where really large base 10 units can be made just by grouping 10 of the previously made units. These larger and larger units are represented by just putting another digit to the left. In a completely by design way, the value of each place in a number is 10 times the value of the place to its immediate right. So tens come from multiplying ones by 10, and hundreds come from multiplying tens by tens, and thousands come from multiplying hundreds by tens. A very common activity seen in elementary classrooms is giving the students large collections of objects. Sometimes it can be snap cubes that snap together. Some teachers are brave enough to use toothpicks, and having the students bundle them into bundles of 10. And then asking the students if there's a way that they could take those bundles of 10 and somehow make them into another bundle. And the students experiment with it. But the accumulation is the students realize that if they have a group of 10 objects, and then they take 10 of those objects that stand for 10 objects, all together, 10 tens is 100. So this drawing represents 100, and then the tens here represent 30, or 3 tens, and then these units here represent 7 units. Now we know, in general, the number 137 represents all of its places taken together. So when we have a string of numbers, such as 137, each digit stands for that many of the place's value. So in the number 137, 1 stands for 100s, or 100, since it's singular. 3 stands for 3 tens, and 7 stands for 7 ones, giving us the number word 100 and 3 tens and 7 ones, which of course we know we can write or say as 130 or 137. Now for a little bit of vocabulary. That string of digits that represents a number, such as 137, is called the base 10 representation, or the base 10 expansion. To help make the base 10 representation a little bit more understandable, we sometimes write it in one of its following forms, and we call those forms the expanded form. So one type of expanded form for 137 would be 100 plus 30 plus 7. Then we could break that down further to 100 plus 3 tens plus 7 ones, as we had above. We were talking about it previously. And then we can break it down a little bit more to another expanded form of 1 times 100 plus 3 times 10 plus 7 times 1. All of these are valid expanded forms for the number 137. It depends on the situation or what you're trying to get across to the students that you pick which one you want to focus on. Now, what the expanded form shows us is how the number 137 in this case is composed of its place value parts. And this is important because although the base 10 system is really efficient and kind of practical, we sometimes have difficulty learning the written names of the numbers because you have to keep the place values in mind. And when the values are not shown explicitly, such as writing the number this way, 137, even interpreting the written numbers, 137 that I have right here, even interpreting the written numbers requires a little bit of abstract thinking on the part of the interpreter. But it is important to remember that using the place value system in base 10, it allows us to write any counting number, no matter how large, using only 10 digits, 0 through 9. And the key idea is to create larger and larger units by just making the value of each new place 10 times the value of the one before it. In this way, using place value, every counting number can be expressed in a unique way as a string of digits. That is simply amazing. Now previously, or actually for this entire lesson, I've talked about counting numbers, and I just want to reiterate, counting numbers are the first numbers that we generally learn to express, I should say. And they generally, or they do, we have defined them mathematically as the set of numbers that begins with 1 and then sequentially increases and goes on forever. Those are counting numbers, and it makes sense because when you're counting on your fingers, you can hold one finger up and say there's 1. Now whole numbers are just the counting numbers with a 0 as its starting point, which is a different ball of wax, because sometimes some children have trouble interpreting what does that 0 represent. I mean, obviously we all know it means nothing. Children understand the absence of things. But how do you represent it when you're working through your problems? And one way to get the idea of nothing being a valid answer or a valid response is to have the whole numbers represented maybe like this, where you start off with a group of nothing, and then you have a group with one number or one dot in it. There's 2, 3, so on and so forth. So they can see that this is an empty container. It has nothing in it. And that, once again, could be a pictorial representation of the whole number 0. Now, there's something else to notice about whole numbers versus counting numbers. Our base 10 system does not make any sense without 0, because 0 is very important in our place value. If you want to write a number such as 200, notice we put 2 zeros there, and those 2 zeros represent the absence of the tens, any value in the tens place, and any value in the ones place. So when we have 200, it means we have 2 in the hundreds place, 2 times 100, plus 0 times tens. We have nothing in the tens place and nothing in the units place. So whole numbers, very, very important in place value. They are very different. Well, I say very different. The concept of 0 is actually quite large. There's quite a bit of historical interest in it if you feel like looking it up. But they are not to be confused. Whole numbers contain 0. Counting numbers do not. Speaking of pictorial representations of numbers, a very common way to represent a number is to use a number line. Now, number lines are excellent for older students, upper elementary. But for students just beginning to learn, number lines can be a bit tricky. And the main reason for that is that a number line is a very specific thing that a lot of us, we just take it for granted. We don't really think about it too much. But on a number line, let me put a heading up here. The way a number line is constructed is we pick a place on this line, and it doesn't matter where you pick it, and we mark that place as 0. So I'm going to mark this place as 0. And then we pick some length down that number line, and we put a tick mark. And I'm going to put it right here. There it is. 1. That's where I put that tick mark. So to the right, there's my first unit. Now notice I have this graph paper as my background. This first unit takes the length of those sides of the square, 2 of them. So if I want to put another tick mark to the right, I would have to count 1, 2 of those little squares to get there. And there's 2 units. And there's 3 units. So number lines depend on length. And what happens if you ask students to find the length of this segment, this is of course a little bit higher up elementary here. If students don't quite keep in mind that a number line is having you actually determine a length of something, a distance of something, they may incorrectly, but quite naively, they're not doing it to be funny, they may say this line segment is 1, 2, 3, 4 units long, because they count tick marks instead of the length. And the length on a number line can be found between tick marks. So this line segment is 1, 2, 3 units long. So how do you help younger students to get an idea of how numbers work out if we decide to show them in some sort of diagram without resorting to using tick marks or grouping objects together in bundles? Well, one method that works really well, I've found in the past, is something called a number path. And we all hopefully know what a number path is. A good example of a number path is playing a board game, and you're moving your pieces along a path with numbers on them. And I think the reason that, for me, number paths work better with younger children is because on a number path, you're counting steps along the path. 1 step, 2 steps, 3 steps, 4 steps, 5 steps, or places along the path. And children are used to that. They count their claps. They're clapping their hands together. They count the jumps they make. They're very comfortable doing that. And this, as you can see, can very easily, when they gain a little bit of mathematical maturity, be turned into a number line. You can talk about how these turn into the tick marks on our number line as we go through it. And number lines are important. Don't get me wrong. Number lines are incredibly important because they're a very nice, concise way to represent decimals or negative numbers. So a number line is essential for elementary students to understand. When you start teaching the concept of how we put these things together into the sequence, a number path is usually, for me, a better way to start off. So I guess the takeaway from this is number lines and number paths are both very, very important. But number lines are interested in length. You're counting the length. And on a number path, you're counting the steps, which is moving from the number line being very abstract. It's not very abstract, but somewhat abstract in how you look at it. If you keep remembering it's a length, it's not too abstract, to something very, very concrete. And if you think about it, as I said, this can very easily transform into a number line. A number path is just an informal precursor to a number line, and it's a nice way to get students used to the idea.